In the late 17th century, Isaac Newton sat surrounded by papers that did not seem to belong to the same man. On one desk lay the mathematics that had helped explain the motions of the heavens. Nearby were notes on light, on prisms, on bodies in motion, on quantities so precise they seemed almost beyond the reach of ordinary thought. But scattered through the same private world were other pages entirely. Notes on prophecy, measurements of the Temple of Solomon, attempts to reconstruct ancient kingdoms, long studies of scripture, corruption, chronology, and hidden meaning to later generations. These pages would seem almost impossible to place beside one another. To Newton, they were not strangers. That is part of what makes him so difficult to see clearly. We inherit a Newton polished into a familiar figure, the severe genius of gravity, the master of reason, the man who turned the universe into law. And yet the deeper one looks, the less complete that image becomes. His scientific achievements were real, immense, and transformative. But they did not bring him to a place of simple satisfaction. Again and again, Newton reached some new clarity and then continued past it, as though the clarity itself were only a surface. He did not seem to believe that nature had given up its full meaning merely because it had yielded a formula. He wanted something further in, something more original, more unified, more final. Perhaps that is the real mystery of his life. Not how he discovered gravity, or how he changed science, but why he kept searching with such intensity after triumph should have been enough. Why would a man who had already explained so much devote years of his life to alchemy, to sacred history, to biblical interpretation, to the architecture of a vanished temple, and to the possibility that truth itself had once existed in a purer form and then been broken apart? What was the single order Newton thought might be hidden beneath light, matter, motion, scripture, and time? And did he ever believe he had truly found it? Long before the world learned to picture Isaac Newton beneath an apple tree, there was a quieter image that mattered more. A young man sits alone in a room, surrounded by loose papers, trying to teach himself how not to be deceived by what things seem to be. That instinct came early. Newton did not move through the world like someone easily satisfied by appearances, and the deeper habit of his mind was already beginning to form long before his great public discoveries gave it a name. He was born in Woolsthorpe in 1642 by the Old English calendar, after his father had already died. His mother remarried when he was still very young and left him for a period in the care of his grandmother. Later accounts of his life would return again and again to the same qualities: reserve, inwardness, sensitivity, and a fierce protectiveness over his private world. Those traits do not explain genius by themselves, but they do help explain the shape Newton's genius would take. He turned inward very early, and over time the visible world began to feel to him less like an answer than a surface. As a boy in Grantham, he was not immediately recognized as the kind of prodigy legend would later invent. At first he was regarded as an ordinary, even weak, student. Then something changed, and he rose quickly until he stood near the top of his class. During this time, he also lodged in the house of the local apothecary, and that detail matters more than it first appears. An apothecary's house was full of mixtures, powders, liquids, instruments, smells, and transformations. It was a place where outward appearance could not be trusted, where one substance might look plain and yet behave very differently under heat, grinding, or combination. That was a fitting environment for the young Newton. Even before he had the language for grand theories, he was already close to a world in which hidden change mattered more than surface form. For a brief period, his family tried to make him into a farmer, but he was plainly unsuited to that life. The routines of land and estate management could not hold his attention the way inward puzzles could. He was sent back to school, and from there eventually to Cambridge, one of those quiet turns in an ordinary life that can alter the history of thought. When Newton entered Trinity College in 1661, he did not arrive as a polished heir to the intellectual world around him. He came as a sizar, under a lower status financial arrangement, and stepped into a university still shaped by older forms of learning. The formal curriculum leaned heavily on inherited authorities, classical study, and Aristotelian philosophy. But Newton's attention quickly began moving elsewhere. Rather than settling inside the approved order of study, he started constructing a private education of his own. By 1664, he was already devoting himself intensely to mathematics and optics, while giving far less energy to the conventional curriculum than Cambridge expected. He began filling a notebook with reflections under the title Questiones quaedam philosophicae, certain philosophical questions. That title reveals something essential. Newton was not yet presenting a finished system. He was training himself to ask in a different way. The world, to him, was not simply something to be inherited from authority. It was something to be reopened. This is one of the most important things to understand about the young Newton. His obsession did not begin with gravity, and it did not begin with the apple. It began with dissatisfaction. The visible world seemed too quickly accepted by other people, too easily named, too comfortably explained. Newton was drawn toward the possibility that beneath ordinary appearance there might exist a deeper structure, something more exact and more universal than the eye alone could ever report. At Cambridge, he encountered Descartes, Boyle, and the newer mathematical spirit beginning to reshape European thought. But he was not simply choosing the moderns over the ancients in some tidy intellectual realignment. What drew him was the promise of hidden intelligibility. He wanted to know whether the world beneath appearances was ordered in a way that could be discovered, tested, and expressed with precision. The notebooks of these years matter because they show Newton before the later image of him hardened into legend, when he was still forming himself through relentless questioning. Then, in 1665, plague shut Cambridge down, and Newton returned to Woolsthorpe. This period would later become one of the most mythologized episodes in the history of science. But what matters is not the romance of isolation by itself. What matters is what isolation allowed. Newton was in his early 20s, already largely self-directed in the areas that interested him most deeply, removed from the routines of university life, and placed in a setting that suited the inward grain of his mind almost perfectly. During these years, from 1665 to 1667, he laid down foundations that would later transform mathematics and natural philosophy. He developed the basis of calculus, made major advances in optics, experimented intensely with vision and light, and even carried out dangerous tests on his own eyes. He also began thinking seriously about the relationship between terrestrial gravity and the motion of the moon. That cluster of work still feels astonishing. Yet what matters most here is not only the scale of achievement, but the pattern beneath it: quantity, light, motion, falling, orbiting, refraction. To many people, these would have looked like different problems. To Newton, they were beginning to feel connected. He did not like isolated facts. He wanted the structure beneath facts, the relation beneath events, the principle beneath the visible world. A curve meant more than its shape. A ray of light meant more than brightness. The moon's path meant more than motion across the sky. Reality kept hinting to him that it was less divided than it appeared. That possibility carried enormous force. If a body falls on Earth and the moon turns through the heavens, perhaps these are not two separate realities. Perhaps the difference between the earthly and the celestial is less absolute than people had assumed. Perhaps one law reaches through both. In Newton, the pleasure of that thought became something stronger than curiosity. Once he sensed that hidden unity might be there, he could not stop looking for it. The apple story survived because it compresses all of this into a single, memorable image. Newton did later connect the sight of a falling apple with his reflections on gravity. But even in the more grounded version of the story, the apple is not the solution. It is only the sharpening of a problem. He saw the possibility that the same kind of force acting on earthly objects might also extend upward to the moon. Yet the full theory did not appear all at once. It would take many more years to work out. That long interval tells us something important about his temperament. Newton was not a collector of dramatic epiphanies. He was a patient inhabitant of unresolved problems. A clue did not satisfy him. It enlarged the search. This is one reason the neat myths about him can be so misleading. The apple suggests completion, but Newton's real habit of mind moved in the opposite direction. He found a hint of order and then spent years trying to discover how far that order extended. Even at this early stage, there was already a certain severity in the way he approached truth. He did not seem content with plausible stories that could not be stabilized by method. He wanted depth, but not vague depth. He wanted what lay beneath appearance, but only if it could be disciplined by evidence, comparison, experiment, and calculation. He suspected that reality was richer than what the senses first delivered, but he also suspected that the mind could deceive itself if it rushed too quickly toward unseen causes. So the hidden had to reveal itself through effects. It had to be approached carefully. When Newton returned to Cambridge as a fellow in 1667, the visible arc of his life seemed to rise very quickly. He took his M.A., continued his work in optics, built the first functioning reflecting telescope, wrote De Analysis, and in 1669 succeeded Isaac Barrow as Lucasian professor. To later generations, this looks like the emergence of the familiar Newton, the young mathematical genius ascending into public importance. But something more interesting was happening beneath that rise. Around the same period, Newton was also setting up furnaces and apparatus for chemical work at Trinity. That detail matters because it shows that the public mathematician and the private seeker of hidden transformations were not separate men belonging to different phases of life. They were already overlapping. Newton was not moving from clear science into later eccentricity. From quite early on, he was inhabiting a larger intellectual world than the later myth would allow. The room of equations and the room of heated matter belonged to the same mind. Mathematics gave him one route toward hidden order. Experiment gave him another. He does not seem to have treated them as enemies. On the contrary, he kept testing whether one mode of intelligibility could reach across very different domains. This is why his early work on optics matters so much to the larger story. He was not merely studying light as one topic among many. He was learning that even what looked pure and immediate to the eye could conceal an unsuspected internal structure. By now, the shape of Newton's lifelong obsession was already beginning to show. He looked at phenomena and sensed that they concealed relations. He looked at relations and suspected they might belong to a wider system. He reached one insight, and instead of treating it as an end, he took it as evidence that something larger might still be recoverable. That is why Newton's life cannot be told simply as the calm accumulation of genius. It has to be told as a search, and a search that deepens each time the world yields one of its patterns. Before Newton could ask what force bound the heavens, he first had to learn a more unsettling lesson. He had to discover that even light itself, the thing that seems most immediate and self-evident, might contain a hidden multiplicity waiting to be broken open. And once he learned that, the visible world could never again feel complete on its own. If light itself could not be trusted, then almost nothing in the visible world could be trusted without deeper testing. That was the unsettling lesson beginning to take hold in Newton's mind. Light seemed simple. It arrived all at once. It illuminated rather than explained. To most people, whiteness appeared pure and complete, the closest thing to an unbroken visual fact. But Newton had already developed the habit of looking at such simplicity with suspicion. The more immediate a thing seemed, the more he felt drawn to ask whether that immediacy was only a surface effect. This was not an abstract preference for complexity. It was a method of attention. Newton did not want mystery for its own sake. He wanted to know whether nature had hidden its structure inside what seemed easiest to accept. And few things seemed easier to accept than light. It filled the room. It revealed objects. It passed so quickly into ordinary experience that people rarely paused over what it was. Earlier thinkers had, of course, argued about vision and color for centuries. Some believed colors arose through modifications of pure light. Others treated whiteness as basic and color as secondary, produced by changing conditions in transparent media or by interaction with darkness. But Newton's experiments slowly pulled him toward a more radical possibility. Perhaps white light was not basic at all. In the quiet of Woolsthorpe and then later in Cambridge, he began working with prisms in a way that was patient, suspicious, and exact. A beam of sunlight passed into a darkened room through a small aperture. It struck a prism. On the wall appeared the now familiar band of color, stretched longer than older theories seemed able to explain. What mattered was not simply that Newton saw a spectrum. Others had seen such displays before. What mattered was that he refused to treat the effect as decorative or accidental. He wanted to know why the image had that shape, why the colors spread as they did, and whether the prism was creating the colors or only separating something already present in the light itself. That distinction became the heart of the problem. If the prism created color, then white light could still be understood as the original simple thing, altered by the glass into different appearances. But if the prism merely sorted rays that were already unlike one another, then whiteness itself would have to be reimagined. Newton pursued the question with a kind of cold persistence. He changed the conditions, adjusted the angles, narrowed the beam, and watched what remained stable. Over time, a pattern emerged that he trusted more than inherited explanation. Different colors were bent by different amounts. Red and blue did not behave identically. The light entering the prism was not uniform in refrangibility, as Newton would put it. It contained distinct rays with distinct properties. That conclusion altered the meaning of color itself. Color was not, in Newton's account, something added to originally pure light by glass, shadow, or corruption. It was already there, hidden inside what the eye had naively called white. White light was not a single untouched essence. It was a compound, and once separated, the colors could not simply be transformed back into one another by further refraction. Their identities remained stable. This gave Newton something more powerful than a striking experiment. It gave him a new model of how nature might work. What appears simple may in fact be composite. What seems immediate may conceal a more organized interior. The senses do not lie exactly, but they compress. This is part of why Newton's optical work mattered so deeply to the rest of his intellectual life. It taught him, with unusual force, that reality could hide multiplicity inside unity. White light looked singular, but it was made of difference, and those differences were not vague. They were regular, measurable, lawful. Nature was not hiding chaos under the surface of appearances. It was hiding structure. That distinction meant everything to Newton. If appearances conceal deeper order, then the task of inquiry was not merely to describe what the eye sees. It was to break visible wholes apart until the hidden arrangement behind them could be inferred. There was also something emotionally satisfying in this kind of discovery. Though Newton would never have put it that way, one can feel, beneath the coldness of the procedure, the quiet intensity of recognition. The world had again confirmed his deepest instinct. It was less obvious than it looked. Its visible smoothness covered an interior architecture, and that architecture was not beyond human reach. It could be coaxed out, not by passively staring at nature, but by putting nature under controlled conditions and forcing it to answer. Newton did not simply observe light. He interrogated it. This was a different posture from the one still common in much older natural philosophy. It was less content with qualities named at a distance, and more interested in what phenomena would do when placed inside a designed experiment. In Newton's hands, experiment became a way of narrowing interpretation. He was not eliminating thought, but disciplining it. The beam was small. The room was darkened. The prism was placed. The angles were adjusted. The result was not allowed to float off into metaphor. He wanted reproducible behavior. He wanted stubborn facts. He wanted a path from appearance to law. That same discipline led him toward a practical problem in astronomy. Refracting telescopes, which use lenses, suffered from distortions that could not easily be ignored. If different colors were bent by different amounts, then a lens bringing light to a focus would not treat all rays alike. A blurred image was not merely a flaw in craftsmanship. It pointed back to the very nature of light. Newton saw that if color separation was built into refraction itself, then no simple improvement in lens making would fully remove the problem. The instrument was struggling because theory had not yet caught up with reality. His answer was characteristically elegant. If refraction dispersed light, then perhaps reflection could avoid the problem. Instead of relying on lenses, Newton built a telescope that used a curved mirror. The reflecting telescope was not just a clever device that helped his reputation. It was an extension of his deeper habit of thought. He had uncovered a hidden structure in light, and then allowed that structure to reshape the instrument itself. The discovery did not remain confined to theory. It altered practice. It changed what one built with one's hands. This is another reason his early work felt so powerful. The world yielded an unseen principle, and the principle immediately reorganized the material world around it. When Newton presented the reflecting telescope to the Royal Society in the early 1670s, it brought him sudden attention. The instrument was compact, impressive, and difficult to ignore. The society soon encouraged him to communicate the work on light that stood behind it. In 1672, he published his famous paper on light and colors. What followed was one of the first major public tests of his intellectual style. Newton entered the learned world not as a modest contributor offering small amendments, but as someone making a strong claim about the structure of reality. White light, he argued, was heterogeneous. Color belonged to the rays themselves. The prism did not paint the world. It disclosed what had been there all along. It is easy, looking back, to treat that claim as an obvious step in the history of science. But at the time, it was not received with quiet gratitude. It provoked resistance, confusion, and criticism. Some readers questioned his reasoning. Others challenged his experimental interpretation. Robert Hooke, already a formidable and difficult figure in English natural philosophy, criticized Newton's ideas sharply. So did Christian Huygens and others in differing ways. What had seemed to Newton a disciplined inference from controlled phenomena now became the subject of dispute. Tone, personality, and wounded pride. This mattered enormously, because it taught Newton something about the public life of truth that he never fully forgot. He had imagined, or perhaps hoped, that if an experiment were carefully designed enough, nature itself would settle the matter. But publication introduced another kind of reality. Results passed through temperaments, rivalries, egos, interpretive habits, and institutional judgments. Newton did not respond to this atmosphere with ease. He was acutely sensitive to criticism and often unwilling to expose himself to repeated public friction. The optical controversy left a mark on him far deeper than the technical disagreement alone would suggest. It reinforced his instinct for privacy. It made him more guarded. It strengthened the division between the work he was willing to release and the work he preferred to cultivate in secrecy. That personal reaction is important to the larger story. Newton's search for hidden order was never only an abstract intellectual process. It was shaped by temperament. The man who believed appearances concealed deeper structure also increasingly believed that public life concealed distortions of its own. One had to protect fragile inquiry from noise, resentment, and premature interference. This does not mean Newton withdrew entirely. He would later publish work that transformed the sciences. But the optics dispute showed him that revelation had a cost. To make one's thinking visible was to submit it to a world not governed by clarity alone. Even so, the central insight did not retreat. If anything, controversy made Newton cling to it more fiercely. He elaborated his arguments, defended the experimental basis of his claims, and kept working. What endured was not just a theory of color, but a lesson about nature. The eye receives white light as though it were something immediate and indivisible. Experiment shows otherwise. Whiteness is a kind of compression, a visual unity built from differences hidden in plain sight. That single discovery resonated far beyond optics. It trained Newton ever more deeply to distrust the apparent simplicity of the world. And once that habit is in place, it begins to spread. If light contains a hidden order masked by ordinary experience, what else might? If the visible world presents blended effects where nature itself contains distinct principles, then inquiry must become an art of separation. One must isolate, test, recombine, and compare. One must discover what remains stable when surface forms are stripped away. Newton's optics did not merely solve a local problem. It refined a style of mind. It showed him that the world could be made to reveal its inner grammar if approached with enough severity. This is why it would be a mistake to treat his work on light as a brilliant side chapter before the greater achievement of gravitation. In one sense, of course, Gravity would make Newton's name immortal in a different way. But optics taught him something more basic about reality itself. It taught him that the world might speak in hidden regularities, and that experiment could teach the mind how to hear them. It also gave him a way to move from sensory confusion toward deeper structure without surrendering to pure speculation. Appearances were not dismissed. They were used, carefully, against themselves. The psychological effect of this should not be overlooked. Every time Newton found that a familiar appearance concealed a precise underlying order, his confidence in the broader search must have deepened. Not confidence in easy answers, but confidence that the search itself was justified. The world was not merely a heap of phenomena waiting to be catalogued. It was intelligible at depth. That belief had now been rewarded in the domain of light with extraordinary force. And because Newton rarely stopped at one successful pattern, the discovery naturally pressed his mind toward a larger question. If white light only seemed simple because many hidden rays arrived together, perhaps motion too concealed a deeper unity disguised by ordinary experience. That is where the optical story begins to open into the celestial one. The same intellectual reflex was now ready to act on a grander stage. Earthly and heavenly motions had long been treated as though they belonged to different orders of reality. The world below seemed mutable, heavy, and corruptible. The world above seemed pure, regular, and set apart. But Newton's work on light had already weakened his trust in such surface divisions. The visible world had once again proved more unified beneath appearances than inherited categories suggested. Why should the separation between heaven and earth be any safer from suspicion than the apparent purity of white light? By this point, the deeper shape of Newton's life was becoming clearer, even if no one around him could yet see its full extent. He did not simply gather discoveries. He moved from one exposed layer of order to the possibility of another. Light broke apart, and the world changed with it. Not only because a theory of color had been corrected, and not only because a better telescope had been built, but because Newton had once more found evidence that nature's smooth surfaces were hiding lawful interiors. The visible world was turning porous under his gaze. It was beginning to admit that what seemed singular might be composite, and what seemed separate might belong to one design. The next step was almost inevitable. If light had yielded this secret, then perhaps motion would yield another. Somewhere between the falling body and the circling moon, Newton sensed that a second great surface division might also be false. And once that suspicion took hold, it would draw him toward the problem that would define his public fame, and still leave him privately unsatisfied. By the time Newton's work on light had begun to change how he thought about visible reality, another suspicion had already started forming in the background. It was quieter at first, less easily forced into experiment, and far more difficult to prove. But once it took hold, it would draw him toward the question that would make his name inseparable from the structure of the universe itself. If nature repeatedly turned out to be more unified beneath appearances than human beings had assumed, then perhaps the old division between the world below and the world above was also a mistake. Perhaps the falling of a body on Earth and the motion of the moon in the sky did not belong to different orders of reality after all. This possibility was radical, not because no one before Newton had thought in large cosmic terms, but because of the scale of the barrier he was trying to cross. For centuries, European thought had inherited the sense that celestial motion possessed a kind of special dignity. The heavens seemed regular, elevated, and set apart. The world near the ground felt heavier, more changeable, more corruptible. Even after the work of Copernicus, Kepler, and Galileo had begun to reshape astronomy, the emotional and conceptual distance between earthly and heavenly motion had not simply vanished. Newton's genius lay partly in sensing that this distance might be an illusion of perspective. Another case in which appearances exaggerated separation, while nature quietly obeyed a deeper continuity. The story is often compressed into the image of the apple, and the image survives because it captures something true in miniature. Newton did later describe how the fall of an apple turned his attention toward gravity, and how that attention widened toward the moon. But the real power of the episode lies not in sudden revelation. It lies in the fact that Newton could look at an ordinary fall and feel the pressure of a much larger question. Why does a body always descend? How far does that tendency extend? Does the Earth's power stop at the surface, or does it reach outward? If the moon is not fleeing into the void, what holds it in its path? These were not separate curiosities for him. They were signs that one problem might be hiding inside another. What mattered was not simply that the moon moved, but that it moved in a way that might be understood as a continual falling. This was one of the deepest shifts in physical imagination that Newton helped bring into focus. A celestial body no longer needed to be sustained by a special heavenly principle. It could be thought of as obeying the same kind of tendency seen in ordinary falling bodies, except that its motion carried it forward so continuously that it never struck the Earth. In this picture, the moon was not exempt from terrestrial reality. It was bound to it, though at a distance. And once that thought became serious, the sky began to look different. It no longer seemed like a separate realm. It became an extension of the same physical world. Yet sensing such unity was one thing, demonstrating it was another. The path from intuition to proof was long, and Newton was not a man who confused suggestive ideas with finished knowledge. The early insight at Woolsthorpe did not immediately become a completed system. One of the most revealing things about Newton's life is that he could hold a great problem in reserve for years, allowing it to deepen, sharpen, and return under better conditions. The attraction of hidden unity did not make him reckless. It made him patient. He wanted the law, not just the image. He wanted a mathematical account strong enough to carry the weight of the world. That demand placed him in the company of earlier thinkers whose work had already transformed astronomy. Kepler had shown that planets moved in ellipses rather than perfect circles, and he had described important regularities governing their motion. Galileo had studied falling bodies and inertia in ways that weakened older understandings of motion. Descartes had offered a grand mechanical picture of vortices filling the cosmos. By Newton's time, the universe had already become a field of intense intellectual reconstruction. But what remained unresolved was how these pieces fit together. How does one move from observed planetary behavior to a general physical principle? What sort of force would account for both terrestrial and celestial motion? Could one produce a framework broad enough to gather these phenomena under a single rule without collapsing into vague speculation? This is where Newton's peculiar combination of imagination and severity became decisive. He could see farther than many of his contemporaries because he was willing to suspect unity where others still saw division. But he could also restrain himself long enough to keep working until the suspicion could be mathematically secured. The old apple story, for all its simplicity, survives because it represents the beginning of that union. A familiar event hints at a universal law, but it was Newton's refusal to stop at the hint that mattered. He spent years carrying the problem rather than prematurely declaring it solved. A crucial development came in 1679. when Robert Hooke wrote to Newton and reopened the subject of orbital motion. Hooke was not an easy man to deal with, and Newton had already tasted the bitterness of controversy through the optics disputes. But intellectual history is not always shaped by pleasant relationships. Hooke's letters helped push Newton back toward a problem he had not abandoned inwardly, but had not yet brought to full maturity. The questions about curved motion, central forces, and the paths produced by attraction regained urgency. Newton later acknowledged that Hooke's correspondence had prompted him into further work on the figure traced by a body under a centripetal force, even through tension and rivalry. The problem began tightening. Still, the decisive movement did not come all at once. Newton's mind often worked by storing pressure until a later moment released it into concentrated form. That moment arrived in 1684, when Edmund Halley visited Cambridge. Halley was younger, energetic, tactful where Newton could be difficult, and deeply aware that something important might be hidden in Newton's private grasp of celestial mechanics. He came with a question that now sounds almost simple. What curve would a planet follow if it were attracted to the sun by a force that decreased with the square of the distance? Newton replied that it would be an ellipse. When Halley asked how he knew, Newton said he had calculated it already. There is something almost unreal in that exchange. It carries the strange quietness often found in Newton's life. A question of enormous consequence is raised in conversation, and the answer already exists in the mind of a man who has not yet published it. Halley asked to see the demonstration. Newton could not immediately find the old papers and promised to send a new account. What followed became one of the turning points in the history of science. Newton wrote a short tract, De Motu, and from there the work expanded until it became the Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The title itself is revealing. Newton was not presenting a local astronomical theory. He was attempting to set down principles broad enough to reorganize natural philosophy. In the Principia, motion would not be treated as a loose field of examples. It would be given laws. Force would not remain an intuitive push or pull. It would become a mathematically analyzable cause of change in motion. The heavens would not stand apart as a special region requiring separate treatment. Their behavior would be integrated into the same framework that governs bodies here below. It was one of the boldest acts of intellectual unification ever attempted. The process of writing the Principia was itself a sign of how Newton worked when a problem had finally ripened to the point of release. What had remained latent for years now unfolded with astonishing intensity. Halley encouraged him, supported the publication, and served not only as admirer, but as practical ally. Without Halley, the book might have been delayed or perhaps never emerged in the form we know. But without Newton's long internal preparation, Halley's encouragement would have found nothing to awaken. The Principia was both sudden and not sudden at all. It was the product of concentrated labor, but also of many years during which Newton had trained himself to see unity where the world offered only scattered motions. At the center of the book was a vision at once severe and almost beautiful. Bodies persist in their state of rest or uniform motion unless acted on. Change in motion follows force. Action and reaction stand in relation. From there, Newton developed an account of centripetal force and showed how inverse square attraction could explain planetary orbits, the fall of bodies, the behavior of comets, the tides, and the subtle perturbations that made celestial mechanics richer than any idealized diagram. It was not merely that one equation applied in many places. It was that the universe itself now appeared as a connected system of lawful relations. For Newton, this was the strongest sign yet that his deepest instinct had been right. Reality was unified beneath appearances. The moon and the apple were not separate stories. The same hidden order passed through both. One could begin with an ordinary fall and end with the architecture of the solar system. One could look upward at the slow-turning heavens and discover that the grandeur of celestial motion did not require a different world, only a wider reach of the same law. That was the intellectual force of universal gravitation. It was not simply another scientific theory. It was a demonstration that nature's visible divisions could conceal an underlying coherence of astonishing scope. This is why Newton's achievement felt so powerful to his contemporaries and to later generations. The Principia did not merely answer questions. It changed the emotional scale of explanation. Suddenly, the universe seemed less like a collection of zones and more like a single intelligible field. The hidden architecture Newton had long suspected was now visible, at least in one tremendous respect. Earth and sky had been bound together. The local and the cosmic had been joined. The search for order had crossed one of the oldest boundaries in thought. And yet, even in the midst of this triumph, something unresolved remained. Newton had found the law. He had shown how the force behaved. He had given the world a framework of enormous predictive power. But what kind of thing was this force? Exactly. How did it operate across empty space? By what deeper cause could bodies influence one another at a distance? These questions did not dissolve simply because the mathematics worked. If anything, the success of the mathematics made them harder to ignore. The more completely Newton described the order of the world, the more strange the underlying agency could seem. That tension was already present in the very greatness of the Principia. The book is often remembered as the moment when the cosmos yielded to law. And it was. But it was also the moment when Newton came closest to a form of explanation that could not easily satisfy the older demand for mechanism. He had turned mystery into precision, but not into final transparency. The force that bound the heavens was real in its effects and undeniable in its consequences. Yet its deeper nature remained difficult to grasp. The hidden architecture had been exposed, but not fully illuminated. For a lesser thinker, this might have been enough. For Newton, it could never quite be enough. His life had already shown the same pattern before. White light, once broken apart, revealed hidden order, now celestial motion, once mathematically analyzed, did the same. But each discovery carried him to the edge of a further question. What lies beneath the law? What sustains the order? What makes the unity of nature possible? Newton could endure long periods of unresolved searching because he was sustained by the sense that each genuine answer was also a threshold. This is what makes Section 3 the true moment of expansion in the documentary's central idea. Newton's search is no longer only the search of a brilliant young scholar testing nature in private. It has become a world-scale act of unification. He has found the strongest evidence yet that creation may indeed be written according to one hidden design. The same mathematical reason seems to stretch from the human hand to the lunar orbit, from the ground beneath one's feet to the furthest disciplined motions visible in the sky. It is one of the boldest confirmations his deepest instinct could have received. But the closer Newton comes to this hidden order, the more he discovers that order does not end inquiry. It intensifies it. A law can be universal and still leave its ultimate cause in shadow. The more magnificent the coherence, the more pressing the question of what kind of reality could sustain such coherence at all. That is why the triumph of gravity is not the end of Newton's story. It is the point at which his public success becomes impossible to separate from his private unease. The force that seemed to bind the heavens had done more than connect the apple and the moon. It had given Newton the most astonishing proof of unity that any natural philosopher of his age had yet achieved. But unity, once found, demanded a deeper explanation than mathematics alone appeared willing to give. And so, even at the summit of triumph, the old pattern returned. Newton had reached an answer immense enough to change the world, only to discover that the answer itself opened into a darker and more difficult mystery. When the Principia appeared in 1687, it seemed to many readers that a new kind of intellectual power had entered the world. The old division between the heavens and the earth had been weakened before, but now it was crossed with astonishing confidence. The same mathematical framework could describe the fall of bodies near the ground, the sweep of planets around the sun, the return of comets, the pull of tides, and the subtle deviations that made celestial motion more complicated than perfect circles. It was one of those rare books that does not merely solve a problem, but changes what a solved problem looks like. Motion itself had become something that could be disciplined into law on a scale that had once belonged only to philosophy or theology. For Newton, this was an immense triumph. The suspicion that had shadowed him for years, that one hidden rule might bind the visible world together across enormous differences of scale, had now received its grandest confirmation. The apple and the moon no longer belonged to separate orders. Earth and sky no longer needed separate principles. A force acting here could also act there. The same mathematical language could pass from a stone thrown by a human hand to the slow majesty of planets turning through the dark. It is difficult to overstate how powerful that simplification was. The universe did not grow smaller under Newton's analysis. It grew more unified. And yet this is where the deeper contradiction of his life becomes impossible to ignore. The Principia gave Newton extraordinary explanatory reach, but it did not give him the kind of final explanation that would have allowed his mind to rest. He had described what gravity does with unmatched precision. He had shown how bodies move under its influence. He had demonstrated, with relentless mathematical argument, that the same force could account for motions once treated as fundamentally distinct. But the deeper question remained. What was gravity? Really, what was acting through space? How could one body influence another across emptiness? The achievement was complete in one sense, and radically incomplete in another. This gap mattered because Newton was not the sort of thinker who could easily ignore it. Some discoveries satisfy by their elegance alone. Newton's did not. Or rather, they satisfied him only up to a point. The law was there. The relations were clear. The predictions held. But the hidden cause still stood partly in shadow. That shadow did not weaken the Principia. It gave the book part of its strange power. Newton had shown that nature could be described with astonishing success, even where the ultimate mechanism remained uncertain. In later centuries, that would become a familiar way of doing science. In Newton's own intellectual world, it was more unsettling. He had reached a summit and found that the mountain continued into cloud. This unsettled others as well. Not everyone who admired the scope of Newton's mathematics felt comfortable with the picture of the world it implied. Some of his contemporaries were deeply troubled by what seemed to be a force acting at a distance, without visible contact, transmitted through no obvious medium, and operating across the void. To many 17th century thinkers, this sounded dangerously close to the very kind of occult explanation the new philosophy was supposed to leave behind. A proper mechanical account, they believed, should show how bodies interact through direct contact, pressure, impact, or some intelligible medium. Gravity, in Newton's formulation, seemed powerful enough to organize the cosmos, yet elusive enough to resist that kind of reduction. This was where admiration became entangled with unease. Christian Huygens, for all his brilliance, did not find it easy to accept such a picture. Gottfried Wilhelm Leibniz, in very different ways, also criticized what he took to be a retreat from true intelligibility. To them, a force acting invisibly across empty space seemed less like explanation than like a mathematical veil placed over mystery. Newton had produced the law. Yes, but had he truly explained the cause? Or had he only described the behavior of bodies while leaving the real machinery of the universe obscure? These were not small objections from the margins. They struck directly at the tension inside Newton's achievement. What makes this moment so revealing is that Newton, in a certain sense, agreed with the discomfort even while defending his work. He did not pretend that the deeper cause of gravity had been transparently laid bare. He was too careful for that. One of the most famous aspects of his mature thought is precisely this restraint. His refusal to invent a mechanism merely to satisfy philosophical appetite. He would not claim more than the phenomena allowed him to claim. If bodies moved according to a definite mathematical law, then that law could be established from observation and reasoning. But the temptation to go beyond that, to imagine a hidden machinery without sufficient evidence, was something Newton increasingly resisted in public. This restraint was not a sign of indifference. It was a discipline imposed on a hungry mind. Newton wanted depth. He wanted hidden order. He wanted causes. But he also knew how easily the mind could deceive itself when it rushed toward unseen entities with too much confidence. So he held the line. He would state the law. He would derive consequences. He would show how the system behaved. But he would not publicly fill the remaining darkness with hypotheses he could not secure. This is one reason his famous methodological caution carried such force. It was not the modesty of a man satisfied with surfaces. It was the severity of someone who wanted more than surfaces, but refused to counterfeit depth. There is something almost painful in that discipline when one places it beside the rest of Newton's life. Here was a thinker who had spent years pursuing hidden structure beneath visible things, and who had just succeeded more magnificently than anyone else in his age. Yet the very success of that pursuit led him to a boundary he would not cross carelessly. Gravity was real in its effects, unavoidable in its consequences, mathematically graspable in its operations, but its ultimate nature remained obscure. That is why the Principia did not close the search. It refined it. Newton had found one of the deepest laws of nature, but the law itself opened onto a more difficult question about what kind of world could be lawful in that way. In this sense, triumph kept turning back into mystery. That was the pattern of Newton's life. The more successfully he described order, the more strongly the problem of order returned at a deeper level. It happened in optics, where white light turned out to conceal a multiplicity invisible to casual sight. And now it happened again in celestial mechanics. The motions of the heavens were no longer governed by separate principles. They had been brought under one rule, but once that unity was achieved, the question grew sharper. Why should the world possess such unity at all? What kind of hidden structure made such elegant mathematical order possible? Newton had not ceased to be a seeker because he had become a lawgiver. If anything, the law only intensified the seeking. The public reception of the Principia also changed the atmosphere around him. Newton was no longer simply a difficult, brilliant scholar working largely in private. He had become a figure whose work demanded response across Europe. admiration came. But so did dispute. Old sensitivities did not disappear under fame. If anything, they grew sharper. Newton remained profoundly reactive to criticism, deeply conscious of intellectual rivals, and unwilling to surrender interpretive ground once he believed himself right. The conflict with Hooke over priority and influence did not merely belong to biography. It formed part of the emotional climate in which Newton defended the integrity of his work. A man already inclined toward privacy had now produced a book too large to remain untouched by controversy. This matters because Newton's intellectual life was never cleanly separable from his temperament. The ideal image of scientific thought often strips away personality, as though truth arrived purified of injury, vanity, fear, or resentment. Newton's life does not allow that simplification. He was capable of astonishing abstraction, but also of wounded memory and hard defensiveness. He wanted clarity, but he did not live in a world made only of clarity. So the Principia entered a social reality where arguments about mathematics could become arguments about authority, recognition, and intellectual legitimacy. That experience deepened a lesson Newton had already learned from optics. Public success did not dissolve obscurity. It created new forms of it. And still, the central philosophical tension remained more important than the personal disputes around it. Newton had shown that the universe could be described as a system of precise relations governed by universal laws. Yet the lawful behavior of bodies did not automatically answer the old metaphysical question of why those laws held, or by what deeper agency the order of the world was sustained. Newton's own language, especially in later years, would increasingly open toward a vision in which divine dominion, cosmic regularity, and methodological caution existed side by side. He would not casually identify God as a substitute for mechanism in the crude sense. But neither was he willing to imagine that the profound order of nature had no deeper significance beyond mathematical description. This becomes especially visible in the second edition of the Principia, published in 1713, when Newton added the general scholium. By then, the book had already made his reputation secure. Yet he still felt the need to frame its meaning more broadly. There he reflected more openly on the relation between natural philosophy and the order of creation. The universe described in the Principia was not a chaos accidentally falling into pattern. It bore the marks of rule, of system, of stable proportion. And for Newton, such features inevitably touched theological questions. The God who appears in the general scholium is not a decorative figure placed at the edge of physics. He is part of the larger horizon within which Newton understood lawful order itself. This does not mean that the general scholium solves the tension. It does something more subtle. It shows that Newton could not leave the meaning of order entirely inside mathematics. The equations described motions. The phenomena fixed the law. But the existence of such a coherent, universal framework still seemed to point beyond itself. Newton was too intellectually severe to blur categories carelessly. Yet he was also too ambitious a thinker to imagine that the deepest questions ended where calculation ended. The result is a picture at once disciplined and restless. He protects natural philosophy from unwarranted conjecture. Yet he also allows the ordered world to retain an almost sacred depth. That is why this section of Newton's life should not be told as though the Principia simply crowned an ascent and settled his intellectual fate. The book did crown something. Certainly, it established his public greatness and transformed the scientific imagination of Europe. But inwardly, it left the main pattern of his mind unchanged. He was still pursuing hidden order. He was still confronting the limits of what could be shown with full security. He was still living in the narrow space between explanation and ultimate meaning. In that sense, the Newton who emerged after the Principia was not calmer than before. He was more authoritative, more famous, more formidable, but not more complete. Perhaps that is the most revealing fact of all. For a lesser mind, success of this scale might have hardened into satisfaction. For Newton, it became another proof that reality could be read, and another reminder that it had not yet been read all the way through. He had bound the heavens and the earth under a common law, but law itself was not the final thing he sought. He wanted the deeper coherence beneath the law, the more original truth that would make the law feel less like a magnificent description and more like a window into the architecture of creation. The Principia brought him closer to that hope than any work of his life. It did not bring him fully to rest within it. And so the great book stands in his story not as an ending, but as a turning point. It proves that Newton can uncover astonishing order without securing final explanation. It teaches him that the world may yield its laws while withholding its ultimate interior. And once that lesson settles in, it becomes easier to understand why his search continues in directions that later generations found strange. If the deepest structure of reality is not exhausted by mathematics alone, then the restless mind that built the Principia may begin looking elsewhere as well, not away from hidden order, but further into it. If the Principia had given Newton a complete and final account of reality, this part of his life would be much harder to explain. A man who had already bound the heavens and the earth under one mathematical law might have been expected to rest in that achievement, or at least to let the rest of his intellectual life settle around it. Newton did not, even before the Principia, and for decades alongside the work that made him famous. He was laboring in another world as well. It was quieter, more secretive, more materially intimate, and far stranger to later generations. In Cambridge, he installed furnaces and experimental apparatus for chemical work as early as 1668 to 1669. Over roughly 3 decades, he wrote and transcribed about 1 million words on alchemy, or what many in 17th century England more often called chemistry. This is the point in Newton's story where the modern image begins to crack open. The man remembered as the supreme geometer of nature was also a reader of obscure chemical texts, a compiler of recipes and symbolic vocabularies, a keeper of laboratory notes, and a patient investigator of hidden transformations in matter. That does not mean he left science behind and wandered into mere fantasy. The categories are not so simple. In Newton's time, the boundaries that later centuries would draw between chemistry, alchemy, natural philosophy, theology, and experimental inquiry were far less settled. To step into Newton's chemical world is not to leave his search for hidden order behind. It is to see that the search was always larger than the polished public image allowed. It helps, first, to resist the easy tone of modern surprise. To us, alchemy often sounds like a synonym for delusion, a theater of false promises about gold-making and mystical secrecy. But 17th century chemistry occupied a more complicated place. It was a field of texts, procedures, substances, furnaces, solutions, precipitates, separations, and hoped-for transformations. It overlapped with medicine, metallurgy, natural philosophy, and practical laboratory culture. It also preserved older ambitions, including the belief that matter contained hidden principles not immediately visible in ordinary experience. That last feature mattered deeply to Newton. He had already learned in optics that what appears simple may be composite, and in gravitation that visible motion may conceal an unseen order. Chemistry offered another domain in which surfaces seemed inadequate. There is something remarkably consistent in that movement. Newton did not enter the furnace room because his mathematical powers had failed him. He entered because mathematics had never exhausted the pattern of his curiosity. He wanted to know whether matter itself contained concealed agencies, latent processes, and forms of activity that ordinary mechanical explanation could not fully capture. This did not make him irrational. In fact, it drew on the same discipline that defined his best work elsewhere. He read closely. He copied obsessively. He compared sources. He indexed terms. He attended to procedure. He gave years to materials that later readers dismissed far too quickly because they no longer resembled the victorious line of modern science. The scale of that labor is one of the most revealing facts in Newton's life. A few stray alchemical notes could be treated as eccentric decoration. A corpus of around 1 million words cannot. The Chemistry of Isaac Newton project makes plain that these manuscripts include laboratory notebooks, transcriptions from earlier authors, and extensive indices of alchemical substances and processes. This was not an idle hobby conducted in the margins of a more serious life. It was a sustained intellectual commitment. And when that fact is placed beside the Newton Project's evidence for the enormous mass of his theological papers as well, the familiar portrait of Newton as almost exclusively a mathematician and physicist begins to look less like truth and more like a later act of selective memory. Yet the interest of this material lies in more than its bulk. What matters is the kind of world it implies. In Newton's chemical writings and reading, matter is not always treated as inert stuff waiting to be pushed from the outside. It is often approached as though it contains hidden tendencies, concealed affinities, and active powers that reveal themselves only under the right conditions. Heat changes things. Mixtures expose unsuspected relations. Dissolution and coagulation become clues to deeper composition. Substances that seem stable in ordinary life begin to show hidden vulnerability in the laboratory. Here again, the visible world proves deceptive. What looks fixed may be transformable. What looks dead may be active. What looks simple may be internally layered. It would be too simple to say that Newton found in chemistry the exact missing mechanism for gravity, or the direct key to all his later thought. Scholars have long debated how tightly his chemical work connects to his mathematical and physical investigations, and there is no single formula that settles the matter. But the older habit of splitting Newton cleanly into a real scientist on one side and an irrational alchemist on the other is no longer convincing. The surviving archives show a thinker working across domains that later ages preferred to separate. His manuscripts make it impossible to dismiss the furnace as a mere detour. The more careful reading is that Newton's various pursuits were connected by recurring habits of mind, even where the exact lines of influence remain difficult to trace. One of those recurring habits was secrecy. Newton's chemical labor unfolded largely outside the public identity by which his contemporaries knew him. He kept this side of his work hidden from many colleagues, just as he kept much of his theology hidden as well. The Chemistry Project describes this as a realm of activity largely concealed from contemporaries and colleagues, even though it spanned around 30 years of his life. That secrecy should not be mistaken for embarrassment alone. Secrecy belonged to the culture of alchemical writing itself, with its coded language, guarded procedures, and layered symbols. But in Newton's case, it also fit a broader temperament. He distrusted premature exposure. He preferred to work ideas into density and complexity before placing them into public circulation, if he ever did. This private mode of inquiry changed the atmosphere of his intellectual life. In the public world, Newton was increasingly the author of lucid demonstrations, mathematical force, and disciplined restraint. In the private world of the furnace, the notebook, and the copied manuscript, knowledge took on a different texture. It became slower, more coded, more dependent on labor with materials and on the interpretation of old authorities. That did not mean it became less exact in his own eyes. On the contrary, he pursued these texts with formidable seriousness. He annotated books, cross-referenced passages, and built up working systems of extraction and comparison. The Newton Project's records of his library and chemical reading show heavy engagement with the vast alchemical literature available to him. He was not dabbling at the edges. He was entering a tradition and trying to master its buried grammar. There is, in that effort, a revealing parallel with his other work. Newton rarely accepted a field at the level of received summary. He wanted to descend beneath polished statements into the structure from which they had been built. In mathematics, that meant working through relations until a law took form. In optics, it meant breaking white light apart. In chemistry, it meant treating old books not as decorative relics, but as encrypted repositories of process, even where the language became symbolic or obscure. Newton behaved less like a dreamer than like a decoder. He wanted to know what the texts were really saying, what operations they hid, what practical truth or natural principle might be concealed beneath the surface language. The pattern is familiar by now. Again and again, he suspects that appearances compress something deeper. That suspicion may also help explain why chemistry would have appealed to him so strongly after the unresolved tensions of the Principia. In public natural philosophy, he had shown that bodies behaved as though governed by forces whose effects could be measured with astonishing success. But the deeper nature of those forces remained difficult to state in chemical thinking. By contrast, matter itself was often imagined as alive with hidden interaction, affinities, attractions, fermentations, and subtle active principles gave substance to a world that was not merely passive extension in motion. Newton did not simply transplant alchemical notions into physics in any transparent way, and it would be careless to pretend he did. Still, the chemical world offered him a rich field in which hidden activity within matter no longer seemed absurd. It seemed investigable. This matters for the emotional shape of the documentary as much as for its intellectual argument. Up to this point, Newton's story can still be mistaken for the ascent of a scientific genius toward public triumph. Section 5 changes the mood. It places us in a more private chamber of his life, one lit not by the polished clarity of published argument, but by long experimental patience and textual secrecy. The atmosphere becomes denser. Newton is no longer only the thinker who makes the world intelligible in a clean and public form. He becomes a man willing to spend enormous stretches of life pursuing truths that remain hidden, difficult, and in some sense still veiled even from him. The search does not become less rational. It becomes less publicly legible. And that may be the most important thing to understand. Newton's chemistry was not a collapse from reason into irrationalism. It was another expression of his refusal to believe that nature had already yielded its full structure. If optics had shown him that light contained unsuspected difference, and gravitation had shown him that motion concealed universal law, then chemistry suggested that matter itself might harbor concealed processes unavailable to the casual eye and not fully grasped by the dominant mechanical philosophies of the day. It offered another depth beneath visible form. That depth may not have produced the kind of public certainty Newton could print under his own name. But it kept faith with the same inner conviction that had guided him from the beginning. The world was not finished at the surface. There is also a quieter human truth here. Newton's hidden laboratory world gave him something the public sphere rarely did. It gave him control over tempo. In controversy, others interrupt. In publication, readers misread. In institutional life, status and noise intrude. But in the workshop of private inquiry, he could move according to the demands of the problem itself. He could gather papers, compare recipes, test substances, and let years accumulate around a single pursuit. For a mind as private and as intense as his, that mattered. The furnace room was not only a place of experiment, it was a refuge for the kind of attention Newton trusted most. By now, the widening movement of his life is unmistakable. The Principia did not bring simplification. It brought expansion. The more Newton succeeded in exposing mathematical order, the less willing he became to imagine that mathematics alone exhausted the deep fabric of reality. Matter itself still seemed to hold secrets. Transformation still seemed to point toward hidden principles. Ancient books still seemed to preserve fragments of knowledge modern readers no longer knew how to read. It is no accident that his chemical work was accompanied by equally vast private labor in theology and sacred history. Once a thinker begins to suspect that truth survives in broken and hidden forms, the search naturally moves across domains. That is where this secret search begins to turn toward its next form. In chemistry, Newton was drawn to the idea that nature concealed operations beneath appearances, and that old texts might preserve traces of lost knowledge in coded language. In religion, a closely related possibility waited for him. Perhaps truth had not only been hidden by matter, perhaps it had also been obscured by history, by corruption, by doctrinal distortion, by generations who had inherited sacred writings without preserving their original meaning. If the laboratory taught him to look for hidden processes, theology would invite him to look for hidden truth. And in Newton's life, those two movements were not strangers. They were parts of the same refusal to believe that the surface of things, whether material or historical, could ever be the final word. By the time Newton's search had carried him through light, motion, and the hidden operations of matter, it was perhaps no longer possible for that search to remain confined to nature alone. If the visible world concealed deeper order, then another question began to press on him with equal force. What if truth had also been hidden in history? What if religion, like light, had once appeared simple only because later generations had forgotten what lay within it? What if the original form of Christianity, far from being clearly preserved, had been altered, layered over, and partly obscured in Newton's life? This was not a decorative side interest. It became one of the largest private labors he ever undertook. The Newton Project estimates that the religious writings now published there amount to roughly 2 million words, a body of work even larger than his already enormous chemical archive. This is the point where the documentary must resist another easy misunderstanding. Newton did not simply become religious in some generic sense after succeeding in science. He had never lived inside that modern division to begin with. For him, the order of nature and the order of creation were never wholly separate questions. The same mind that distrusted appearances in optics and mechanics also distrusted inherited certainty in doctrine. If the world had to be interrogated to reveal its hidden structure, perhaps scripture and church history had to be interrogated as well. The search for truth could not stop at the boundaries later centuries would draw between physics and theology. In Newton's hands, both became parts of a larger effort to recover what had been concealed. One of the clearest signs of this private seriousness came in the 1670s, when Newton faced the expectation that, as a Cambridge scholar holding the Lucasian chair, he would normally proceed toward holy orders. In 1675, he obtained a royal dispensation exempting him from ordination. The Newton Project notes that the likely reason was his private dissent from Trinitarian doctrine. That detail matters because it shows how early and how deeply his theological convictions had already formed. He was not drifting casually through orthodoxy while thinking private thoughts at the edges. He was protecting himself from an institutional commitment that would have forced him publicly into a formula he could not honestly affirm. The search for truth had already become dangerous enough to shape the practical structure of his life. What Newton appears to have believed, though he guarded it carefully, was that Christianity had undergone corruption very early in its history. The doctrine of the Trinity, in his view, did not belong to the original teaching of Christ and the earliest church. It was a later distortion, imposed through ecclesiastical power, textual manipulation, and doctrinal confusion. Because these views were politically and religiously dangerous, he shared them only with a narrow circle. The Stanford Encyclopedia and the Newton Project both emphasize that Newton's anti-Trinitarian convictions remained largely secret, even though they shaped an immense portion of his theological labor. This secrecy was not incidental. It was part of the moral atmosphere of his search. If truth had been corrupted, then the seeker of truth had to move carefully through a world still governed by the corruption. There is something unmistakably Newtonian in the way he approached this problem. He did not merely declare dissatisfaction with doctrine in a mood of rebellion. He went to work on texts. He compared manuscripts, traced variants, reconstructed arguments, and tried to determine where and how corruption had entered. In 1690, he sent John Locke a long study, later known as Two Notable Corruptions of Scripture, arguing that major Trinitarian proof texts had either been forged, altered, or persistently misread. The Newton Project describes this analysis as both a sign of his doctrinal commitments and an example of his extraordinary ability to generate a detailed and innovative tract in a short time. In other words, Newton approached sacred corruption not with vague suspicion, but with the habits of a textual investigator. This is one of the deepest continuities in his life. In optics, he had separated white light into distinct rays and shown that the apparent purity of whiteness concealed difference. In theology, he now treated orthodoxy in a strangely similar way. What appeared unified and settled might in fact be a later compound, a historical mixture whose elements needed to be separated if one wished to recover the original truth. That does not mean theology was merely optics by another name, but the habit of mind is unmistakable. Newton did not trust smooth inherited surfaces. He wanted to know what had been blended together, what had been added, what had been lost, and whether the original form could still be recovered through disciplined analysis. The corruption of religion, like the hidden composition of light, became a problem of penetrating appearances. His relationship with Locke reveals another important aspect of this hidden world. Newton did not trust many people with his most dangerous conclusions, but he trusted Locke enough to share an extended textual case. That act suggests not only intellectual confidence, but also the loneliness of his position. To hold such views in late 17th century England was not merely to differ in private. It was to stand near forms of heresy that could destroy reputation, office, and security, Newton had every reason to be cautious. The Newton Project points to the later public downfall of figures such as William Whiston as a reminder of the danger. In that sense, secrecy was not simply psychological preference. It was a form of survival. Yet Newton's theological labor was about more than negation. He was not only attacking corrupt doctrine, he was trying to recover original religion, again and again. His manuscripts returned to the idea that pure truth had once existed in clearer form and had been obscured over time. The corruption of Christianity, in his view, was historical rather than metaphysical. Truth itself had not vanished. It had been overlaid by councils, priests, partisan readings, and institutional power. That made recovery thinkable. And once recovery becomes thinkable, the work of scholarship changes its emotional tone. One is no longer only criticizing errors. One is searching for remnants, fragments, and buried continuities that might still lead back toward the source. This helps explain why Newton's theology expanded so naturally into church history. Prophecy, sacred chronology, and the interpretation of biblical books such as Daniel and Revelation. If corruption had unfolded across time, then truth could not be restored by proof texts alone. One had to understand the history of the church, the rise of false authority, the sequence of empires, the symbolic language of prophecy, and the way scriptural meaning had been refracted through centuries of dispute. The Newton Project's catalog of manuscripts makes the scale of this clear. Drafts on early church history, extensive studies of prophecy, variant readings in Revelation, and notes on the Temple of Solomon all belong to the same broad effort. Newton was not collecting eccentric curiosities. He was assembling a map of sacred order across time. At this point, the public image of Newton and the private reality of Newton begin to separate almost completely. Publicly, he was the author of the Principia, the great master of law, force, and mathematical order. Privately, he was also a scholar of heresy, textual corruption, prophetic symbols, ancient religion, and the long deformation of original Christianity. Later generations preferred the public Newton because that figure seemed cleaner and easier to place inside the story of modern science. But the manuscripts make the cleaner story increasingly difficult to sustain. Newton did not think of truth as distributed into neat modern departments. The hidden order he pursued reached through matter, motion, scripture, and history alike. There is a subtle but important difference. However, between Newton's public caution in natural philosophy and his private boldness in theology. In physics, he famously refused to invent mechanisms he could not securely ground in phenomena. In theology, he was willing to reconstruct long narratives of corruption and recovery. But even there, he worked through documents, variants, chronology, and comparative reading rather than pure assertion. He remained, in his own way, a disciplined mind. The difference was not between rigor and fantasy. It was between kinds of evidence. In religion, the evidence came through texts, councils, inherited doctrines, and historical traces. Newton read those traces with the same intensity he brought to nature, convinced that beneath the official surface lay a more original truth. And perhaps that is what gives this part of his life its unusual emotional force. Newton is often remembered as a man who made the universe colder, more mathematical, more impersonal. But the theological manuscripts reveal something else. They reveal a man for whom truth was not merely a matter of successful description. It was also a matter of fidelity. Error was not only intellectual, it could be historical and spiritual. to recover original religion was, in that sense, a moral act. The same hunger that would not let him stop at the visible order of the world also would not let him rest inside inherited doctrine if he believed that doctrine had betrayed its source. This is why Section 6 matters so much to the central argument of the film. Newton's obsession is no longer only the search for hidden order in nature. It becomes the search for hidden truth beneath corruption. The governing pattern remains the same, but its field has widened. The world below appearances is now not only mathematical and material, it is sacred and historical as well. Once that widening takes place, the next movement becomes almost inevitable. If truth has been dispersed across prophecy, sacred architecture, and the rise and fall of civilizations, then Newton will be drawn toward the question of how divine order has been written into time itself. And that is where his search becomes wider still. The God of order is no longer only the remote author of a lawful cosmos, nor only the original source of a corrupted religion. That God has also, Newton believes, left traces in sacred measurement, prophetic sequence, and the architecture of history. The path from scriptural corruption leads naturally onward, toward Solomon's temple, toward Daniel and Revelation, and toward the attempt to read time itself as though it too were part of the hidden design. Once Newton had come to believe that truth in religion had been corrupted and partly buried beneath centuries of doctrine, his search could not remain confined to isolated passages of Scripture. If original truth had been damaged across time, then time itself became part of the problem. The history of kingdoms, the rise of churches, the sequence of empires, the symbols of prophecy, and even the measurements of sacred architecture all began to matter to him as parts of one larger pattern. The Newton Project's overview of his religious writings shows just how extensive this field became. Prophecy, Jewish worship, Solomon's temple, church history, and chronology all belong to a single broad body of work, rather than to scattered eccentric interests. This is one of the strangest and most revealing widenings in Newton's life. He had already treated nature as something whose visible surfaces concealed hidden order. Now he began treating history in a similar way. Events, dynasties, doctrines, and biblical symbols were no longer merely things that had happened or texts that had been inherited. They became clues. Time itself seemed to carry structure beneath confusion. The same mind that had looked at motion and suspected a universal law now looked at prophecy and sacred history and suspected a design that had to be reconstructed, piece by piece, from corrupted remnants. The Temple of Solomon became central to this effort. To a casual reader, the temple might seem like a devotional or antiquarian sideline. For Newton, it was neither. The Newton Project notes that he worked extensively on the dimensions of Solomon's temple and on the practices of the people who worshipped there, and it has published manuscripts specifically devoted to the temple and the sacred cubit. This was not idle symbolism. Newton believed that measurements mentioned in Scripture, especially in prophetic contexts, could carry figurative meaning and reveal a deeper order. Sacred space was not merely a setting for religion. It was itself part of the language through which divine truth had been expressed. That detail matters because it shows how Newton's habits of mind continued to move across domains without losing their shape. He had always been drawn to the thought that visible things might conceal a more exact interior. In the temple manuscripts, measurement itself becomes a path toward hidden meaning. Lengths, proportions, and units are not treated as accidental details. They are approached as signs of order, One can feel the same intellectual temperament at work here that had earlier refused to let white light remain a simple visual fact. For Newton, sacred architecture also had to be opened, analyzed, and read. The structure of a building could become a fragment of revelation. From there, it was a short step into prophecy. Newton wrote extensively on Daniel and Revelation, and the surviving manuscripts make clear that he did not read them in a casual or purely devotional manner. In one treatise on Revelation preserved by the Newton Project, prophecy is described as a sealed script that must be opened and interpreted through hidden predictions and open allusions. Elsewhere, Newton treated prophetic books as systems of vision and interpretation whose symbols had to be matched carefully with historical developments. He was not looking for a burst of private inspiration. He was trying to build rules of reading. Prophecy, in his hands, became a disciplined attempt to connect symbolic language with the long movement of history. This is where the documentary should slow down and notice the consistency of Newton's method. He did not merely believe that the future had been foretold. He believed prophetic language had structure, and that the structure could be approached rationally. The temple, the beasts, the horns, the days, the kingdoms, the sealed books, all of these belonged to a field of coded meaning. Newton wanted not just the meaning of one passage, but the architecture that made the meanings cohere. He was still the same kind of thinker he had been in optics and gravitation. He was still trying to move from appearance to underlying system. The difference was that the system now stretched across scripture and history rather than across light and motion alone. The Newton Project's introduction to the texts offers one especially important detail here. It notes that Newton believed dimensions mentioned in Old Testament prophecy could bear figurative meaning, and gives the example that prophetic days meant real years. That single point opens a great deal. It shows that Newton's reading of prophecy was not literal in the simplest sense. He was not flattening scripture into straightforward chronology. He was instead treating it as a symbolic system governed by rules of correspondence. Time in prophecy was one thing on the page and another thing in history. The visible text, once again, concealed a deeper ratio beneath its surface. This symbolic historical method also helps explain why chronology became so important to him. If prophecy mapped the broad sequence of corruption, empire, and restoration, then chronology offered the framework within which that map could be tested. Newton's chronological studies were not a separate late hobby tacked onto the end of an otherwise scientific life. They were bound up with the same effort to discover the true order of sacred and ancient history. The Newton Project lists major manuscript groups and printed texts tied to chronology, and later scholarship has emphasized how closely Newton's chronological studies were linked to his prophetic work. What Newton sought in chronology was not simply a list of dates. He wanted the real sequence of ancient civilization. That meant questioning inherited timelines, reconciling biblical and classical materials, and compressing what he believed had been artificially extended by unreliable traditions. According to Oxford scholarship on the chronology of ancient kingdoms amended, the posthumously published book caused a storm of controversy in 1728 because Newton drastically contracted Greek history by about 500 years and Egyptian history by about a millennium. This was not minor adjustment. It was a radical reshaping of antiquity by one of the most famous minds in Europe. That controversy is important not only because it shows Newton making bold historical claims, but because it reveals the scale of the order he was seeking. He was not content to discover a universal law in celestial motion and leave the past to inherited confusion. He wanted ancient history itself to become tighter. cleaner, more intelligible. The same impulse that had once moved him to ask whether one law could bind the apple, and the moon now moved him to ask whether one corrected framework could bind scripture. Classical antiquity and the rise of kingdoms. History, in his hands, becomes something like a damaged manuscript that can still be restored if one is severe enough in method and patient enough in labor. There is also a striking overlap here with Newton's interest in ancient religion. The Newton Project notes that after the first edition of the Principia, he wrote on the religious and scientific practices of the ancients, and that these materials were related both to his larger treatment of ancient religion and to draft classical scholia he once intended to include in a later edition of the Principia. This is an extraordinary clue. It shows that, in Newton's own mind, the study of ancient worship and belief was not sealed off from the grand work of natural philosophy. The worlds of cosmic order and ancient religious truth were still close enough to touch. That closeness tells us something fundamental about his imagination. Newton did not think the ancients were simply primitive people waiting to be corrected by modern science. At times, he seems to have suspected that traces of profound knowledge had once existed and then been lost, fragmented, or disguised. This does not mean that he imagined ancient wisdom in a naive or romantic way, but it does mean that he was open to the possibility that truth was older than the institutions currently claiming to possess it. In that respect, his studies of antiquity and prophecy belong to the same moral and intellectual pattern as his attack on doctrinal corruption. Original truth lay further back, buried under later accretions. The emotional tone of this phase of Newton's life is worth noticing. By now, he is not only a seeker of laws, but a restorer of hidden continuities. The world he inhabits privately is one in which measurements, manuscripts, empires, and symbols all seem to point beyond themselves. A temple dimension can speak to prophecy. A prophetic number can reshape history. An ancient kingdom can become a marker in a sacred sequence. To modern habits of thought, this can feel unnervingly wide. But for Newton, the widening did not mean losing rigor. It meant following order wherever it seemed to leave traces. He was still trying to bind scattered things into one intelligible frame. That is why the phrase architecture of time fits this part of his life so well. Newton was not merely arranging dates. He was looking for structure in history itself, just as he had looked for structure in light and motion. Sacred architecture taught him that space could embody hidden meaning. Prophecy taught him that symbols could encode historical sequence. Chronology taught him that the past could be reconstructed as an ordered framework rather than received as a mass of confused inheritance. Together, these pursuits made time feel built rather than merely endured. The centuries were no longer only a flow of events. They became a patterned field that might still disclose design. There is a quiet audacity in that vision. Newton had already unified heaven and earth under one mathematical law. Now, in private, he was attempting a different kind of unification. He was trying to join sacred text, ancient architecture, prophetic symbolism, and civilizational history into one readable order. The ambition is almost overwhelming when seen whole, and yet it grows naturally from the life we have been following. Newton kept discovering that apparent divisions were weaker than they looked. White light concealed multiplicity. Earth and sky obeyed one law. Orthodoxy concealed corruption. It is entirely consistent that he should finally suspect that time itself also concealed a deeper coherence. Still, the effort did not end in universally accepted truth. Newton's chronology was controversial. His prophetic interpretations remained private or posthumously influential, rather than publicly canonical. His temple studies did not reorganize learned culture the way the Principia had reorganized natural philosophy. In that sense, this phase of his search is more fragile and more haunting. It shows him pursuing an order that the wider world was less willing or less able to receive. The hidden design seemed real enough to him to justify decades of work, yet it did not emerge into shared certainty with anything like the force of universal gravitation. That contrast is part of what gives Newton's later life its peculiar grandeur. He did not stop where recognition was easiest. He went on looking in places where method became harder, where the evidence was older and more damaged, and where the recovered order would always be more debatable. But he kept looking because the inner pattern of his mind had not changed. Truth still seemed hidden. Surface inheritance still seemed inadequate. And the hope of a deeper coherence still seemed strong enough to justify immense labor. He had become, in effect, a historian of concealment as much as a discoverer of laws. By the time we reach the end of this section, Newton's obsession has widened as far as it can go without becoming the question of his legacy itself. He has sought order in light, in force, in matter, in doctrine, in prophecy, in sacred space, and in the sequence of civilizations. What remains now is to ask whether these were truly separate pursuits that happened to coexist in one extraordinary life, or whether they formed one long search whose unity later generations preferred not to see. The Newton inherited by the modern world was brilliant, austere, and clear. The Newton emerging from his manuscripts is larger, stranger, and much harder to contain. When Newton died in 1727, he left behind more than the works that had already made him famous. He also left an enormous private archive, much of it unpublished, much of it difficult to classify, and much of it devoted to subjects later generations would not know how to fit beside the Principia. The surviving record makes that scale impossible to ignore. The Stanford Encyclopedia notes that across roughly 60 years of intense intellectual life, Newton put no less effort into chemical and alchemical research and into theology and biblical studies than he put into mathematics and physics. The Newton Project and the Chemistry Project have made that reality even harder to evade by showing the sheer volume of the material. About 1 million words on chemistry, and roughly 2 million words of religious writing published through the Newton Project's editions. That fact alone changes the emotional shape of his legacy. For a long time, the Newton most people inherited was the Newton of polished achievement, the author of the laws of motion, the master of universal gravitation, the architect of a mathematically ordered universe. That Newton was real, but he was never the whole man. The fuller archive shows a figure whose life was spread across public science, private theology, chemistry, chronology, prophecy, sacred history, and textual criticism. The difference is not minor. It means that the modern image of Newton was not exactly false, but it was narrow. It preserved the part of him most useful to the later story of scientific modernity and let the rest remain in shadow. Part of that narrowing happened because Newton himself helped create the conditions for it. He published selectively. He fought fiercely over certain public arguments, but left many of his most revealing private labors outside print. The Newton Project's work repeatedly shows that some of his most extensive theological and prophetic writings were written for an audience that remains partly mysterious. while the chemistry project stresses that he kept much of his alchemical work largely hidden from contemporaries and colleagues. That meant that the Newton available to public memory was always, from the beginning, only a partial Newton. Posterity did not invent the split entirely. It inherited a life already divided between visible achievement and guarded manuscripts. Even so, later generations deepened that divide. The cleaner Newton was easier to celebrate. He fit the story of reason overcoming obscurity, mathematics disciplining nature, and modern science emerging from older worlds of symbolism and theology. The stranger Newton did not fit so neatly. A man who wrote on prophecy, sacred chronology, temple measures, and chemical transformation sat awkwardly inside the image of the pure scientific genius. The result was a long period in which much of the archive remained either unpublished, understudied, or treated as an embarrassment rather than as part of the main intellectual story. Modern editorial and digital projects exist in part because earlier habits of memory had left so much of Newton's world only partially visible. That recovery did not happen all at once. One of the great turning points came in 1936, when the Portsmouth Papers, a large surviving portion of Newton's manuscripts, were sold at Sotheby's. The Newton Project's account of that sale makes two things clear at once. The auction broke up the archive, which was a loss, but it also revealed, more publicly than before, the full extent of Newton's interests in alchemy and unorthodox theology. Cambridge's digital collections likewise note that Newton's papers were sold at auction in 1936. In other words, the dispersal of the manuscripts was also the beginning of a more unsettling visibility. The simpler Newton became harder to sustain once the papers themselves started to circulate more widely. This is one of the ironies at the center of his legacy. The archive had to be fractured before the larger shape of Newton became easier to see. What had long remained hidden in family holdings and partially inaccessible bundles now drew the attention of collectors, scholars, and later editors. The Chemistry Project points out that the 1936 Sotheby's catalog described hundreds of Newton manuscripts, with more than a third of the lots unmistakably alchemical. It also notes that some of these papers had earlier been regarded as not fit to be printed. That phrase captures, almost perfectly, the discomfort Newton's private work inspired. The very materials that now seem indispensable to understanding him were once treated as the part of him most easily pushed aside. From that point onward, Newton's legacy became harder to keep inside a single story. The public Newton remained overwhelmingly powerful. He still transformed mechanics, optics, and the mathematical sciences. Nothing in the recovered archive diminishes that. But the archive changes what those achievements mean when placed inside a full life. The Principia no longer looks like the serene endpoint of a purely scientific ascent. It looks instead like one magnificent expression of a much wider intellectual hunger. Newton did not stop with universal law because the discovery of law had never exhausted the kind of truth he sought. The manuscripts do not make him less great. They make the scale and character of his greatness harder to simplify. This is also where a careful documentary has to resist a newer simplification. It would be easy to swing from the old sanitized Newton to an opposite caricature, as though the hidden archive proved that he was really something other than a scientist all along. That is not a serious reading either. The point is not that Newton's physics was a mask and his real life lay elsewhere. The point is that the same man moved across domains that later centuries separated more sharply than he did. The Newton Project's introductions repeatedly stress that the newly available writings make it possible to understand links between strands of his religious work and their possible links with other areas of his intellectual life. That does not settle every question of unity, but it does make the old split between the real Newton and the other Newton far less convincing. So what, then, is the Newton we inherited? In one sense, we inherited the most publicly victorious one: physics classrooms, schoolbook legends, and the ordinary cultural memory of science still present Newton above all as the thinker who reduced the motions of the world to law. That inheritance is justified, but incomplete. In another sense, especially over the last several decades, we have begun inheriting a different Newton as well, one restored through manuscript scholarship, archival editing, and digitization. The Newton Project now publishes all of Newton's writings, whether printed or not, and the Chemistry Project makes his alchemical papers legible as a serious body of work, rather than as a curiosity. Modern recovery has not replaced the familiar Newton. It has widened him. That widening changes the meaning of the whole life we have been tracing. The young Newton who distrusted appearances in light. The mature Newton who bound earth and heaven under one law. The private Newton who searched furnaces. Scripture, prophecy, temple measures, and ancient chronology now appear less as a collection of mismatched episodes than as recurring expressions of one habit of mind. Again and again, he found that visible surfaces were not final. White light concealed difference. Celestial and terrestrial motion concealed unity. Orthodoxy concealed corruption. Historical inheritance concealed damaged chronology and buried sacred order, even if we cannot reduce every manuscript to one neat formula. The overall movement of his life shows a remarkable consistency. Newton kept pressing past what the world seemed to be toward what he believed it might more deeply reveal. That is why the phrase "one idea" still matters, even after all the complications. It would be too crude to say that Newton spent years obsessed with gravity alone. It would also be too crude to say he was only obsessed with religion, or only with alchemy, or only with some vague dream of total truth. The stronger interpretation is that he was haunted by the possibility of hidden order itself. Not just order in one domain, but order that might run through domains. An underlying intelligibility, a creation whose scattered parts might still belong together. His achievements did not cure that obsession. They fed it. Every time reality yielded one of its patterns, Newton had reason to believe that another pattern still waited behind it. And perhaps that is why the later archive feels so moving, not merely surprising. It does not show a great mind drifting into irrelevance after triumph. It shows a mind unable to stop asking what triumph had really disclosed. The laws of motion explained immensely much, but not enough. Gravity bound the cosmos, but did not tell him everything about cause. Scripture preserved truth, but not in an uncorrupted form. Ancient history remembered the past, but not in a sequence he found trustworthy. Again and again, Newton reached something real and then found that reality still receded into depth. The unfinished quality of that pursuit is part of his legacy too. There is also something revealing in the way modern institutions have had to rebuild him through manuscripts. The Newton Project at Oxford was created to publish all of his writings, including the theological ones, and has since expanded to provide detailed transcriptions across the scientific and mathematical corpus as well. Cambridge's digital collections and the Indiana Chemistry Project have likewise made the dispersed papers more accessible. This means that the fuller Newton now arrives not through legend, but through editorial labor, transcription, comparison, and the slow assembly of a broken paper world. In a strange way, that is fitting. Newton himself spent his life treating fragments, clues, and difficult texts as the path toward hidden order. His own afterlife has required something similar. What remains, then, is not a tidy verdict, but a more honest inheritance. Newton was the author of one of the greatest scientific books ever written. He was also a private scholar of religion, prophecy, chronology, and chemistry on a scale that long remained obscured. He helped create the modern world, yet he also kept company with older ambitions that the modern world later tried to leave behind. The recovered archive does not force us to choose between those truths. It asks us to hold them together. And when we do, Newton no longer appears smaller for having been stranger. He appears larger, more difficult, and more human. So, the order he sought may never have arrived in the fully unified form he hoped to find. Or perhaps it arrived only in fragments, each fragment convincing enough to keep the search alive without ever bringing it to final rest. But that, too, is part of what he leaves behind. Not only laws, methods, and discoveries, but an image of inquiry that does not stop where success becomes respectable. Newton spent his life trying to discover whether the world, scripture, and history were pieces of one hidden design. The modern age inherited the laws most easily. Only later did it begin to recover the depth of the question that had driven him all along. In the end, Newton left behind more than a set of discoveries. He left behind a way of longing. That may sound unusual for a man so often described in terms of logic, discipline, and proof. But there was something in him that was never content to stop where explanation became respectable. He could take the visible world and reveal its hidden regularities with astonishing force. He could show that the heavens were not a realm apart, but part of the same order as the falling objects of the earth. And still, that was not enough. His mind kept moving toward what seemed older, deeper, and less settled, toward first meanings, toward lost truths, toward the possibility that the universe was not only lawful, but interpretable in some more complete and sacred sense. Perhaps that is why Newton still feels larger than the image history tried to fix around him. He reminds us that curiosity is not always neat. It does not always stay inside the borders later generations draw around knowledge. Sometimes it moves outward, and sometimes inward. Sometimes it solves. Sometimes it complicates. Sometimes it reveals that the more clearly we understand one part of reality, the more strangely the whole begins to shimmer beyond it. Newton spent years pursuing a hidden order he may never have fully possessed. But there is something quietly moving in that unfinished search. It suggests that the deepest scientific hunger is not only the desire to measure the world, but to ask whether its fragments belong together, and whether behind the many surfaces of things there waits a pattern still just beyond our reach.